Okay, and so concerning the deliverables, so we set up a planning, some deliveries and milestones to say, okay, this is more important than this second step. We put all the software in the versioning controls. This is also something you have to do normally in a software project. What was provided to the users? So a C++ executable. So you can see that as an executable IC. Some release notes and user guides for sure. Also the unitary tests passed on the IPs and the subsystem test. So basically you provide the platform with a simple example on the ARM cores to reach the main function, and the same on the EVP. And then the guys, they have something up and running and can type in and start really to use the platform. For sure you will have bugs. Sometimes it's in the software running on top of the platform, sometimes it comes from the models. So you have to do, and we did every week a CCB meeting, so a change control board meeting. So through this meeting we reported into a tool all the problems, all the change requests that either the architects wanted or the end users. So this project in fact lasted around 10 months. So it was 1/3, 2/3 between the IP created and reused. So we created Viterbi and Turbo decoder based on C code we already used before. We created this radio interface unit to make the communication with the reference tester. We needed an interrupt controller and some clock generation unit that were not used at the beginning but later on. So again, using the SCML library, it's really easy to go fast to create models and to set up the platform quickly. So this was really the target. So after around 1 month, we had the ARM Cortex R4 available with the VPU, the interrupt controller, and the RU. So all the blocks were not finished, but we already had enough to start the validation of the RX path with soft bits. So it means that we bypass in fact the EVP processing and directly put samples, soft bits samples at this part in the simulation chain. Then we received the first release from Coware and started to do the RX validation pass on the IQ samples. And then we refined our models until reaching the end. So a small example on how to create a functional unit. So the radio interface unit, so as I told you, using the SCML, you first need to define a target port here. Then this target port is mapped to a registers bank, which is an SCML memory object. And so at this time already you see your blocks like a real IP. I mean like in VHDL. Then you will have the callback function attached to the registers, and so it means that when you do a write access or read access to registers, it will trigger automatically a callback function, and so you know exactly where to put your implementation and how to react on the write and read accesses on the registers. And also one point that I did not mention is that this block will be part of PCT somewhere in the memory map, and so the address decoding is done automatically by the tool. So you just have to say, okay, I want this block at this address. Then if you access this block, like it was the case by the ARM, this block was a slave in fact on the bus. The decoding is done for you. So you just have to set this interface. Okay, on the other side we have the AXI port. So this port was used to be connected to the interconnect, and these blocks transport the data from the tester to the input memory of the EVP. So this was done through this port. Here we see the UDP socket. So this port was used to exchange the packet of data with the tester. So you communicate with the tester, sending and receiving packets on the internet network. Here we see 3 signals. So it was transmit and RX interrupt. So we have 2 paths, one for release 99 samples and antenna, and the other one for HS DPA. And so basically when data were available from the tester, we just trigger an interrupt to wake up the EVP and say, okay, you have now to process some data. I have some data for you. Here what I said before, the read DMA and write DMA. So yeah, you imagine that samples have to be written somewhere, to be also copied from the EVP output memory back to the RU and returned to the tester. And so this was done by this DMA. But again, in this case we did not instantiate DMA. It was directly a code typed in the block inline. So the reference tester, so as I said, it was the night tester. So this is hardware, this is also hardware. And the link we used was this one. So the IQ over IP. So the ABP is the night baseband processor. So this is provided by a night, and you exchange data using this link. So this slide is extracted from a presentation from a night. What is also really convenient is that then when your IC is available, you will reuse the test written using this tester with the virtual platform, and just have to replace the virtual platform by the final IC. Tester is also capable to exchange and communicate using radio frequency with the mobile phone. Here we see 5% the real time. So normally the virtual platform is slower than the tester, but the speed is automatically adjusted by the tester in case you are fast. So it means that you can imagine to save, for example, some sample somewhere, and then reach the same point in time more quickly using this automatic throughput adaptation from the tester. So you decide at the beginning if the virtual platform will send first data to the tester or if it is the opposite. So you have some initialization phase, or you will decide okay, which one is sending first, how many data you will receive in each packet. So you can send up to 266 IQ samples at a time. And then once this is done, you just have an acknowledge from the tester saying, okay, I'm ready, everything is perfect, we can start. And so then you send your IQ data, for example in this case, to the tester, and the tester will answer, and you go like that into your test.